Now that we're in lesson 24 through 25, we finally get to learn about linear systems. So we're going to start by graphing a couple of equations and taking a look at what that tells us. So first we want to start with graphing both of these equations right here. 2x minus 2y equals negative 4 and y equals a negative x minus 4. This first equation, because it's in standard form, we're going to graph using the intercepts. So if we're going to graph it by the intercepts, remember, we're going to cover one of them to find that intercept first. So if I want the x-intercept, I'm going to cover up y. I'm essentially going to take away y. 2x equals a negative 4. And that tells me that, well, 2 times what gives me a negative 4? That would be a negative 2. So x equals negative 2. There is a point where the line crosses the x-axis at negative 2. So right here. Next, we do it the other way. Cover up x. And see what we got. So we have a negative 2y equals negative 4. Well, what times negative 2 gives us negative 4? Positive 2 would. So the y-axis, it's going to cross at positive 2. So here we have a point, and now we have 2 points so we can draw our line. So this is the first equation. Now let's go ahead and graph the second equation. The second equation is y equals negative x minus 4. That is in your y equals mx plus b form. That's your slope-intercept form. So we're going to graph it using the intercept and then go from there with using the slope to find a second point. Our starting point is the y-intercept, which on here is negative 4. So that tells us on the y-axis we start at a negative 4. And then the slope is negative 1, which tells us we can either think about going down 1 to the right 1, or you can think about going up 1 to the left 1. Either way, that's still going to give you that negative slope. And now that we have more than 2 points, we can draw our line. So here we've graphed both equations, and we can see that they cross. So the next it asks us, where do they cross? At what point do they cross? Well, they cross right here in the middle. So we have a crossing point right here at negative 3, negative 1. But why does that matter? Why would we care that they cross at negative 3, negative 1? What would be so special about that point? Well, if we remember back to thinking that every single point along a line is a solution to that equation, so everything along the black line is a solution to the first equation, and everything along the red line is a solution to the second equation, maybe where it crosses, this is a solution to both equations. Let's check it out. Let's see if that's true. So let's try the first equation. The first equation was a 2x minus 2y equals a negative 4. So I want to see if negative 3, negative 1 is a solution. And I'm going to do that by plugging them in. So we have a negative 3 for x, and we have a negative 1 for y. So that becomes negative 6. This becomes positive 2. And this is still negative 4. Does negative 6 plus 2 equal negative 4? Yes, it does. So that was a solution to the first equation. Let's check the second equation. The second equation was y equals negative x minus 4. We have negative 1 for y. So negative 1 goes in for y. We have a negative 3 for x. We still have that negative 4. So we still have a negative 1. Negative 3 becomes a positive 3 minus 4. So does negative 1 equal 3 minus 4? Yes, it does. So we just proved that that point where they cross is a solution to both equations. So let's take a look at what the actual definition is of linear systems, considering the fact that we actually just did one. So a linear system is a set of 2 or more linear equations. So if you have more than one equation, we call it a linear system. Now, in this level of math, you're mostly going to see just 2 equations being used for a system. In high school, you'll probably see a little bit more of 3 or 4, but you could have 1,000 equations as long as you're graphing them together and finding that singular place where they cross. You have a linear system that you're working with. So then what's the solution to a linear system? The solution is where the lines cross. And we just saw that where the lines cross is a very special point. That is the point that is a solution to both equations. So now let's write down a couple examples of linear systems. There's a couple ways you might see it done. You might just see you might just see two equations essentially put on top of each other like we just saw. So maybe you have an x plus y equals 6 and a y equals negative 2x plus 3. That can be considered a system, but sometimes you'll see brackets on the outside. A lot of times you'll see kind of brackets like this with the two systems inside. So maybe you'll have 2x plus 3y equals 10 and 6x plus 7y equals 5. So sometimes you'll see it like this, and sometimes you'll see it with this bracket on the outside. And that's just to say everything that's inside this bracket is this. And again, you could see more than just two. So you could have one that's like this with three systems on the inside. So this also would be a system, and you would graph all three of those. And you're looking for the solution, the numbers, the point that works in all three of those. So let's actually try solving a system now that we know actually what we're doing. So now we're going to solve the system that has the equation 2x plus 5y equals 10 and y equals 2x minus 3. So remember, the solution to the system is where those lines cross. We're essentially looking for the point that works in both of those equations. Now, solving by graphing is not the only way to solve for these, but it is the first and most fundamental way of solving that you can always go back to. So let's start with plotting just this first equation. We have 2x plus 5y equals 10. Because that's in standard form, we're going to graph it based on its intercepts. So if I want the x-intercept, I'm going to cover up y. 2x equals 10, so x equals 5. So that tells me there is a point at the x-axis where x equals 5. So on my x-axis, 1, 2, 3, 4, 5, there's a point. Now I'll do the same thing for y. So if I want the y-intercept, I'm going to cover up x. I have a 5y equals 10. Well, what times 5 gives me 10? So y is 2. So that means on the y-axis, we have a point where it's 2. Now that we have 2 points, we can draw a line. Now, I just want to pause and say an important tip. Since we are dependent on our graph in order to find the solution, you're going to want to make sure that your graphs are as accurate as possible. So even though I always tell you that 2 points is enough to draw a line, you might want to start doing 3 or 4 if you're solving by graphing, solving systems by graphing, because if your lines are off, then your solution is going to be off. So let's graph the second equation. We have a y equals 2x minus 3. That's in our slope-intercept form. So we're going to start with the intercept, which is negative 3. That tells us that on the y-axis we have a point at negative 3. And then our slope is 2, a positive 2, which means we go up 2 over 1. And remember, we might want to do a couple times to make sure this is accurate. Now that we have a couple points, we can draw our line. So remember, the solution is where they cross. So now we can see that they cross at 2, 1, and that is going to be our solution. So we got that our solution is 2, 1. Now if we really wanted to check our answer, we could take the points and throw them in and see if it works in the equation. Now, one of the reasons I don't like solving by graphing is it really only works if my solution really is whole numbers. Because it's hard to tell if that really is 2, 1 or maybe it's 2.1 and 0.9. So this is why, yes, graphing to solve is very fundamental, but I do not prefer it as far as always finding the absolute correct answer. It really does depend on your numbers being whole numbers. But it is the first way that I will be teaching you. Later on, I'll be teaching you solving by substitution and solving by elimination. So now let's move on and look at systems being applied to an actual problem. So we're now going to take a look at a word problem and see how that works with systems. Now, we've solved word problems before by writing an equation and solving for an unknown. This is very similar, but when you're using a system, you're going to have more than one unknown. So as a rule, you need as many equations as you have unknowns. So if you have 2 things that you don't know, you're going to need 2 equations to work with. If you have 3 things that are unknown, you need 3 equations to work with. So this is why before, when we had 1 unknown, we could just work with 1 equation and find out what that was. But now we're going to have 2 unknowns, so we're going to need a system. We're going to need 2 equations to solve for that. So let's find out what our situation is here. 2 small pitchers and 1 large pitcher can hold 8 cups of water. Ooh, that already tells me something. It's telling me that we have 2 small pitchers and 1 large pitcher. If you add together what's in it, it's going to be 8 cups. So we can write an equation from that. So 2 small pitchers, so maybe I want to put an S, plus 1 large pitcher equals 8 cups. All right, so we already have one equation that's equaling out our total amount of cups. Let's look at the rest of the situation. 1 large pitcher minus 1 small is 2 cups of water. Well, we can easily write an equation from that as well. 1 large pitcher, so that's a large, minus a small is 2 cups equals 2. How many cups of water can each pitcher hold? So now we have our 2 equations for our 2 unknowns, so we can find out both of them. So we're just going to need to graph both of these in order to find out what the solution is. Now, when we wrote our equations, we used L and S as our unknowns, and you, of course, are allowed to select any variables that you want. But then when it comes time for graphing, you have to decide which one you want to be X and which one you want to be Y. It really won't matter as long as you recognize when it comes time to look at the solution which one's going to be which. So maybe my X will be the small one and my Y will be the large one. So let's put that on here. So my Y is the large pitcher and my X is the small pitcher. So the first equation, 2S plus L equals 8. Maybe it might be a little hard for me to think about that now in terms of graphing, so I want to rewrite that with my X and Y. So this we can think of as 2X plus Y equals 8. And same thing for my next one. I have a Y minus an X equals 2. Now this looks a little bit more familiar for us to graph with. Now they're both in standard form, so we're going to use the intercepts on both of them. So this first one, if I want the x-intercept, I cover up y, 2x equals 8. Oh, so the x-axis, it crosses at 4. So at the x-axis, down here is 4. And if I want the y, where it crosses at y, the y-intercept, I cover up x. Well, y equals 8. That's convenient, right there. So now we can draw a line between those. Now if I want my second one, I'm going to do the same thing. If I want the y-intercept, I cover up x, y equals 2. That's easy enough right here. And then if I want the x-intercept, I cover up y. Negative x equals 2, so x crosses at negative 2. I guess I'm going to have to draw that in on my graph because I actually don't even have that. So right here at negative 2. So that means I need to go up 2 over 2 to get to my next point. So maybe I want to draw one more point on here just to make sure I'm going in the right direction. And a lot of you can see we've already kind of discovered where they cross. So remember, where they cross is our solution. So they cross at 2, 4. So we have to take a look at our solution and see what it means as far as what was happening. Because saying 2, 4 is a solution is not what it's asking. It's asking how many cups of water each can hold. Well, x was my small, so that means that the small pitcher can hold 2 cups of water, and the large pitcher can hold 4. It's always good to look back at the actual problem to see if your solution makes sense. If you're getting a number and just writing it down, and you're not thinking back to what it's actually asking, you might be missing a secondary part that you're supposed to solve, or you might have messed up somewhere and you're not seeing it because you're not making sure it makes sense in the problem. So for us, a large pitcher holds twice as much as a small pitcher. Yeah, that seems about right. And also kind of makes sense in our equations, the fact that the large pitcher minus the small pitcher equals 2. So remember, we can always throw these back into the equations to make sure it really is a solution. Last thing we're going to talk about is special solutions, because of course never anything in math is always going to be that simple. There's always going to be exceptions to the rule. So we're going to take a look at 2 types of special solutions. You might be thinking that you might already know what these are, considering there are 2 different types of special solutions to linear equations, so maybe linear systems are the same. Let's take a look. So I need to graph this system. 6x plus 3y equals 9. So if I graph by the intercepts, cover up y, we have a 6x equals 9. All right, divide both sides by 6. And x equals, what is that, 1 1/3. So I'm going to come here. X is 1 1/3. Do the same thing for y. So I'm going to cover up x, 3y equals 9. Well, 9 divided by 3 is just 3, so it crosses y at 3. Now we have 2 points, but remember we might want to do a couple more just to make sure we're accurate, especially since we have one that's a fraction. So my slope is that I have to go down 3 to the right 1 1/3. So let's do that again. If I go down 3, I'm here, and then I need to go to the right 1 1/3. Well, 1 1/3 plus 1 1/3 is 2 2/3. So I need to go to 2 2/3. And this will make it so that my graph's a little bit more accurate to have 3 points, especially when I'm working with fractions. All right, so we have the first equation. Now we need to graph the second equation. So the second equation is also in standard form, so we're going to use the intercepts. 2x to cover up y, so we have a 2x equals 3. So if I want my y-intercept, I do 3 over 2, which is 1 1/2. So x crosses at 1 1/2. And then if I want my y-intercept, I cover up x, y equals 3. Something's looking a little special here. Well, I have my 2 points again if I wanted to do the same thing. Uh-oh. Something special is going on with this line. I ended up with the exact same line. Now, if I have the same line and my solution is where they cross, but they're on top of each other, aren't they crossing everywhere? So wouldn't everything be a solution? You're absolutely right. There is infinite solutions here because they are the same line. So because they are the exact same line, they of course have similar solutions all along there. So you're going to have infinite amount of solutions that can work in both of those. Let's take a look at one more special solution, but I bet a lot of you can figure out what it's already going to be. Here we have y equals 2x plus 6 and y equals 2x plus 3. So they are in slope-intercept form. If I'm going to graph this first one, I'm going to start at 6. 1, 2, 3, 4, 5, 6. And then my slope is 2, a positive 2, but I don't have room to go up, but I can go down instead. So remember, you just have to do 2 negatives to keep it positive. So I could go down 2 and to the left 1, because that keeps my positive slope. Down 2 to the left 1 keeps my positive slope. So now that's definitely enough points for us to have an accurate line. Let's draw that in. So we now need to graph the second equation. We have a y equals 2x plus 3. So since that's in slope-intercept form, we're going to start at positive 3. So the y-axis at positive 3. Then the slope is 2. So I'm going to go up 2 over 1, up 2 over 1, or I could go down 2 to the left 1 if I wanted to. And that's definitely enough points for us to draw a line. Let's draw that in. Something interesting is going on with this set of equations. They aren't crossing. Now, sometimes when this happens, it might be that I'm just not graphing the right part of the equation, but it doesn't look like they're ever going to cross because they're constantly the same distance from each other. There's a name for that. It's called parallel. And you can let me know if that's spelled wrong. So we have parallel lines, but the solution is where they cross. But parallel lines never cross. So I'm never going to have a solution. So there's no solution. Now, a fast way to figure out if there's no solution if the lines are parallel without graphing is by looking at the slopes. Parallel lines have the same slope. So if you're given this set of equations and you're supposed to graph it to solve, but you see right away that they both have the same slope, they both have the slope of 2, then you can already tell that it's going to be parallel and that it has no solution. So that's going to be a shortcut to not have to graph it if you see that right off the bat. And that is actually the end for this lesson.
Hi, Mom.